is Dr. Brian Van Eschen from the Lawrence Livermore National Lab. Many of you might be knowing him. He is leading a lot of work called the project he will be introducing, which is called LBANN. So mostly focusing on the deep learning at scale for scientific computing. So he's the informatics group leader and a computer scientist at the Center for Applied Scientific Computing at LLNL. He's pursuing research in large-scale deep learning for scientific domains and training deep neural networks using high-performance computing systems. He's the project leader for the project I indicated, LBANN, which is an open source learning toolkit, and the LLNL lead for the exascale computing project called XRLearn and the Candle project. And additionally, he also co-leads an effort to map scientific and machine learning applications to neural network accelerator, coprocessor, as well as neuromorphic architecture. So he joined Livermore in 2010 after earning his PhD and master's in computer science and engineering at the University of Washington. And he also has an MS and BS in electrical and computer engineering from CMU. So with this, let's welcome Brian. Brian, please share your slides and get started.
Okay, great. I think you need to make my, I'm logged in from two systems because my computer doesn't have a camera, and actually let me turn off this light behind me. So can you make the other username the presenter?
Okay, just
there we go.
Okay.
And then share my screen. Wait, it has disabled host disabled NT screen sharing.
Can you please try now?
Let me try now. Okay, we're getting there. Let me just find the right application.
Okay.
Oh, it's going to force me to log right back into Zoom on this computer. So let me do that. I apologize.
Not a problem.
All right, I'm logged back in now.
Are you still a panelist? Okay, let me try to promote you. I think you should be a panelist now.
Great.
On both accounts.
Okay. And then share.
Yes, perfect. Thank you.
Great.
All right, awesome. You'll see the presenter view. All right, so thank you very much, Dr. Panda and everyone for inviting me to be the keynote. It's my privilege to talk to you about some of the work we've been doing at the Center for Applied Scientific Computing on deep learning at large scale. And what I'm trying to do is talk about some of the communication challenges and opportunities that we've been seeing in several application areas that we are focused on. I would like to start by saying and thanking all of the great researchers and developers who've been contributing to this project over the better part of 5 to 6 years. Many of these are Livermore staff, some are student interns, including Arp and Jane, who we had a fantastic time hosting virtually this summer, and others, Nikolai Dryden and Yosuke Oyama at both ETH Zurich and Tokyo Tech. So it is my privilege to present their work and share with you what we're trying to do. As you guys all know, deep learning is absolutely everywhere. It's becoming a standard data analysis tool, but the challenge, especially for scientific applications, is the data sets and the data samples themselves are growing much, much larger than previously, than in previous generations. And these can be because we're looking at 3D volumes from simulations. We can be looking at time series. We're pushing the dimensionality, higher resolution, more spectral channels, so you get a greater depth of your data cube. And fundamentally what happens is that as you push these limits, your tools are going to break down in one dimension or another. And I'm going to go through a couple of those dimensions, but also our approaches to solving those. But fundamentally, fast training is critical to be able to actually do the science that you need, develop new neural network architectures, and train them on these data sets. But for some of these, you can't even get out of the gate unless you do distributed deep learning. And as at the MPI user group or the Mbappage user group here, I guys know it's near and dear to your heart, but distributed algorithms are fundamentally critical to how we go forward in the next generation. And so it's a really exciting time to talk about distributed deep learning and what the requirements are. And just if the previous slide wasn't scary enough in terms of what's going to happen, we have new scientific instruments in the open science domain that are coming online that are producing absurd amounts of data volumes every day, every night. And so we are data rich. There's certainly no loss of opportunity to be able to train deep neural networks and teach them on these models. But again, any one of these samples or let alone data sets is going to challenge the common frameworks that we use day to day, and we need some new solutions. And so I'm going to talk to you sort of about 3 research areas that our group has been working on that all relate to how do you train either large models or large data sets or data sets with large samples. And I'm going to try and break it down into these 3 main categories and talk to you about different solutions that we've developed in our toolkit, really focusing on what some of the data motion communication challenges are. And so this will sort of be our outline for how we go through it. I've laid out both the challenges for each one as well as our proposed solutions. So we'll come back to this slide as sort of a milestone or goal post marker as we go through the talk. The framework we're talking about is one we've developed in-house at Lawrence Livermore and across a couple of other national labs and universities. It is the Livermore Big Artificial Neural Network Toolkit, LBANN. And fundamentally, it is an alternative to PyTorch or TensorFlow, but it has been designed for distributed memory algorithms and implementations of training using HPC systems with distributed algorithms. As such, it's built on a GPU accelerated distributed linear algebra library called Hydrogen, and also a high performance GPU-aware communication library called Aluminum that we developed a couple years ago that helps us wrap the different communication protocols that we are playing with and make the compute and communication streams integrate very well so that we can interleave those communications and get the best performance from our systems. It has a PyTorch-like based front end. It supports open model exchange using systems like Onyx. And it really is a mixture of C++, MPI, OpenMP, CUDA, and we're embracing the AMD software stack now again. So we have ROCm and RICL in there as well. And all this work is open source on GitHub, and we welcome academic and industrial and government collaborators. As you can see on the right-hand side, we have the whole soup of different communication protocols from MPI, CUDA-aware MPI to other things like NVIDIA's Nickel or RICL, as well as other programming models like NVSHMIM for different applications. And we're trying to enable users to use these in the most efficient way possible without actually having to understand all the nitty-gritty details of how they need to move their data. This is a cartoon representation of what a distributed deep learning might look like. The URL for where LBANN is up on top left there. And the idea here is that we are going to be optimizing for the entire stack, all the way from when you're bringing in data from a parallel file system, caching it in large system memory or in VRAM on each node. Layers are distributed in both data parallel and model parallel striping across multiple nodes and multiple GPUs per node, and all of the communication is hidden or is encapsulated nicely inside of the LBANN toolkit. So when you write your model, you don't actually have to sweat all these details. And one of the key parts here is this, one of these middle level bullets here is being able to seamlessly combine multiple types of parallelism, model, data, and ensemble parallelism, because neither one will scale indefinitely. And there's a lot of challenges as you want to do that. And really we're focusing on a combination of both strong and weak scaling of our problems. So efficiently training with larger data sets, but being able to run down the wall clock time to train a single model, because sometimes you just need to get one model well converged to do the science that you want. So we're going to start with one of the biggest problems we have, which is when you have large neural networks, we have a huge number of network parameters, either large numbers of convolutions, fully connected layers, or a lot of the new tension-based models like the sequence-to-sequence transformer family, where you have a very large number of parameters. And we're going to focus first on how you deal with distributing convolutions efficiently for these models, and this will drive towards both a traditional large models like wide ResNet, and then we're going to go into how you deal with transformer models and large spatial domains as well in our second challenge. So what's the problem is, so data parallelism is an absolutely fantastic mechanism for scaling up your calculation and making it run more efficiently, as long as it continues to work. And the idea, I'm pretty sure everybody in the audience is familiar with, is you put different, you spread your neural network across multiple GPU accelerators, you give all of them some number of samples, but not the full data set, and you use collectives like an Allreduce to be able to sum up the gradient contributions on backward propagation so that all the models are identical as you go through time. And this is great because it has the minimal amount of communication, but it turns out this is not a knob you can turn forever. So as you increase the batch size, shown here on for a ResNet model, two different data sets, ImageNet and OpenImages, x-axis is the batch size, y-axis is the number of steps required to train to reach a particular validation error. What you see is the scaling behavior starts to fall off, where the models don't learn as efficiently, and eventually actually they may not even converge with very large batch sizes. So this knob does not continue to work indefinitely. So what are your options when your data parallelism is run out? Well, we presented some work on how to deal with spatial parallelism at IPDPS in 2019. This is a great way to work, and we're going to show its application for a 3D volume in about midway through the talk here. But the idea is, rather than partition the data into whole samples and give them to different accelerators, give each accelerator part of the sample and treat it like a stencil computation with a halo exchange. So the halo is shown here in red, and this allows you to compute the same mathematical result as if it could fit on the entire on a single accelerator, but you can work with samples and models that don't even fit on a given GPU or TPU or whatever your accelerator of choice is. However, this does not work if there are small spatial domains or a large number of parameters. And also, it doesn't really address some of the challenges of doing large Allreduces. And so what we're going to talk about in more depth for this talk is how can we deal with different types of decomposition for generalized parallel convolutions. Just to give us a little bit of a common visual framework here, so we can see an image of different samples, cats and dogs, shown here in their spatial extent, H and W, as well as their channel depth. And we have in samples of those. Inside our neural network, we have different filters, each of which is K by K by C, and you have F of them. And then you create these activation maps at each layer of your neural network, where you have the result of the filter applied to those input samples, and then you just stack this up. So as we go through some of the different algorithms that change dramatically our communication patterns, you're going to see we're moving different parts of these different tensors, and which tensor you want to move varies greatly based on the size and dimensionality of the tensor. So I'm going to go into more depth here for channel and filter parallelism. This is work we presented at SC last year, back when we could have real conferences. Unfortunately, this year's will be virtual, but I'm sure it'll be spectacular. And so the idea here is that you can parallelize in either the channel or the filter dimension. And this leads to a family of algorithms that we refer to as stationary X, Y, or W, based on which matrices don't move and what data is communicated. And this is really coming from matrix multiplication literature when we talk about stationary X. And in fact, we're going to show that to achieve an optimized performance and implementation of this, we're going to jointly partition the channels and filters to find the right balance of partitioning. And this is going to allow us to do two things. One is partition parameters to get the most out of our GPUs, but it's also going to allow us to use segmented Allreduces, which allow us to minimize the sort of the spatial domain over which these communication patterns are happening. Not necessarily the spatial domain in terms of the model or the input, but the number of accelerators that are participating in any given collective operation. And so this is going to allow us to strong scale our convolutional neural networks, which are at the heart of many of the key networks we see today, decrease the all-reduce overhead. However, there is always an increase in communication required. And so when you look at these results, your evolution of what you want to do is, if data parallelism gets you there, do that and stop. Otherwise, you can go into these more complex and sophisticated approaches to parallelization. The other thing is that, to the best of our knowledge, LBANN is the only toolkit right now that supports these types of partitioning schemes. There are some similar work in both mesh TensorFlow and FlexFlow, but not as rich nor as encompassing nor as scalable as what we have to offer. Okay, so let's just look at our favorite model here, ResNet 50, or not necessarily our favorite, but a common model here. And the idea is that as you go deeper into the neural network, you end up with a large number of channels that provide you with an opportunity to do either channel or filter parallelism, and limits the efficacy of spatial partitioning, as we've shown in previous work. And so hybrid parallelism is not a new concept. This is not something we developed from scratch. We're standing on the shoulders of giants here. So Krzyzewski, he actually showcased this in his AlexNet paper back in the dark ages, the emerging of the new age in deep learning in 2014, when we hit our most recent renaissance for the use of deep neural networks. But the idea here was, and he pioneered this, was mixing both data parallelism and channel and filter parallelism as well. They did it again to fit within the 3 GB memory constraints of the GPUs they had in their laboratories. And so we're taking this same idea, and we are providing a little bit more formalism around it, and also extending it to thousands of GPUs to be able to train even larger models. It is important to note, as you evaluate how your neural networks might map onto these architectures, is that it's very common to have some amount of data redistribution partway through your neural network. As I said, and actually let me grab a pointer here. Sorry, laser pointer. This part of the neural network is amenable to data and spatial parallelism, and so you want to use that. And then you'll do a redistribution and implement data and channel, data plus channel or filter parallelism in the deeper parts of the neural network. And we're going to use the same technique when we get to our performance results. Okay, so we're not going to go too deep into the actual implementation of the description of the data movement, but I did want to give you a very quick overview, and these are all in our SC19 paper that Nikolai Dryden was the first author on. The idea is that we're going to represent our tensors in something like a NCHW format or an NFHW format as well. And we're using a circle to note that that is the dimension over which we are distributing. So here in this X tensor, we have a data parallel scheme where we're distributing over the number of samples, and everything else is replicated. And then we have this nomenclature where you say when you do your convolution in the forward direction, you can see what kind of data motion we have, similar for the backward data and backward filter updates. So this is generally the notation you see. And as I said, we're not going to go into more depth in this, but you'll see this algebra on the left-hand side of the slides as we talk about what are some of the opportunities for communication, which ones do we rely on heavily. And of course, the hope here is that allows library communities like in Babbage to really identify what are the critical workhorses and where are there opportunities to have a high impact in distributed deep learning. So as I said, there's 3 algorithms we're going to go through in high level here. The first of which is a stationary X algorithm, where the input samples for a given layer they do not move, and you're going to communicate the error on the backward propagation phase. You can do the reverse of that, a stationary Y, where if your error signals are going to be larger, you're going to keep them in place, and you're going to distribute your input, activate your inputs to each layer, or you can do a combination called stationary W, where you're moving everything around. When we look at the stationary X, this is an example again where we have each sample is distributed over 2 GPUs. So here's sample 1, sample 0, and here's sample 1. Here are the filters shown here in the middle column. And as we do the forward convolutions, we produce our activation maps. And as we go to compute our error, we're going to do reduce scatters to get the information that we need at the end of this phase of network training. When we go backwards, we're going to use all gathers to collect the results and redistribute it back into the layout that we need. And then everything from there is fairly straightforward to compute the gradient updates. But as I said here, one of the key aspects of these kinds of algorithms is that we start to introduce segmented Allreduces, where the filters are not uniformly distributed across the GPUs. And so there are fewer ranks participating in each of these Allreduces. And at large scale, that allows us to get much more effective communication. Here's that in a little bit more detail here. And so just the idea is, again, that you can, essentially have or continue to reduce the number of participants for these Allreduces. And as we scale to, in this example, 2,000 GPUs, this was work done on LBANN, the unclassified little brother of the Sierra supercomputer at Lawrence Livermore National Lab. It's a Power 9 system with 4 voltas per node, and about a little over 700 or close to 800 nodes now. What you can see here is that as we increase the number of GPUs from 2 all the way up to 2,000, pure sample parallelism, you can see here is the cost to do a single all reduction with just straight sample parallelism. And as we add more levels of segmentation, this is for a network with 128 by 3 by 3 by filters, you can see noticeable improvements in the cost for that all reduction. And that's going to play out at large scale for the end-to-end application performance. And again, this is a communication pattern that we could see some improvements on. We think there should be greater than the sublinear improvements, but it's an opportunity for the libraries to help out at. So now we move on to our stationary Y algorithm, and it's going to feel very similar, except we're going to start with the data samples partitioned. And then we're going to do an all gather to give everybody a copy of that within the 2 GPUs on top and the 2 GPUs on bottom for the samples. So I'm sorry, this is everybody gets the filter channels that they need. The rest of your forward algorithm is as you expect, no communication once you've done that first all gather. And then on the backward phase, again, you're going to do a reduce scatter to take those filter maps and those error maps and distribute them back to the GPUs from their temporary buffers. And then again, more segmented Allreduces in order to do the updates to the convolutional filters. And finally, stationary W, as I said, this is the combination of both of these two approaches. And so what is happening here is we're going to do all gathers up front to collect the channel maps, produce the intermediate results from the filters, which are also distributed here. As you can see, not all 4 filters are on each GPU. They are replicated or they are distributed, reduce scatter at the back end. And then when we do the backward pass, it is again a set of all gathers, and you can sort of see how the error map from this first and third row here get shared to GPUs 0 and 2, and likewise for 1 and 3. And again, once you get the temporary values, you can see a similar reduced scatter, but now we're within the same GPUs. And finally updates to the kernels. So what I'm hoping you guys are seeing in this opportunity here is that we can basically bring a lot of the very traditional HPC communication libraries and parallel programming techniques to deep learning to great effect, which I'll show you in a couple slides here. But it does sort of drive new use cases within the deep learning training and inference application space. So when do you want to choose a stationary X versus Y? Is often you want to keep that largest tensor stationary. Oftentimes it's the stationary X is most beneficial, but sometimes Y depends on the channel growth and whether you're doing upsampling. And so that really depends on the actual application your network is trying to learn. And similarly, stationary W gives you more parallelism, but requires more memory requirements and more communication. So there is a balancing as a toolkit vendor of how do we expose and allow these different algorithms to be used by the users without making their heads explode. And this is sort of just a sum up of the 3 different key approaches we have to how do we handle both data and now spatial and finally channel and filter parallelization for convolutional neural networks. Particularly the spatial and channel filter allow you to strong scale training of a single sample, which is incredibly important, as you'll see when we talk about 3D cosmological volumes. And you can see that it's a combination of halo exchanges or different collectives from reduced scatter all gathered to Allreduces or segmented Allreduces. Okay, so what did we run this on? As I said, this work was all done in the LBANN toolkit. It used a library called DisConv, which has now been fully integrated back into the mainline code. We used custom communication and packing kernels. We used a combination of the different vendor libraries, particularly cuDNN and cuBLAS. This work was done at FP32. This was done up to 512 nodes, and you can see the node architecture here of a LASSON compute node. The idea is that when you do 2-way partitioning, you can keep it local to 2 GPUs on a single socket. 4-way will take the whole node, and anything above that will use InfiniBand and the Mellanox adapters. I will say that good detail to the topology of what you're mapping to and how you map ranks down is another critical aspect to making sure this performs well. So let's talk about how ResNet performs with data parallelism. So we here show an increase in mini batch size and on the x-axis and the total time for a mini batch. And we're going to look at this column here, which represents strong scaling. So we're going to keep the global mini batch size fixed regardless of the number of GPUs being used. And as we see data parallelism, as it's increasing the mini batch size, the time per mini batch goes up because of the ever increasing overheads in the Allreduce operation. So when we do a two-way stationary X algorithm, you can see that at small scale on the left hand of this graph, we don't see any performance benefit, and that's fine. Data parallel is doing okay. But as we get to larger and larger mini batch sizes, we start to see a clear separation where the stationary X starts to perform better. And this is really the segmented Allreduces allow us to get more efficient computation. When we combine the two-way spatial stationary X with spatial partitioning, we get actually a nice jump in overall performance, because we're now, each GPU is doing a smaller set of the problem, and as long as we balance the cost of that computation versus the communication overheads, we can see a win. And this is really, smaller channel domains. We're now actually fully into this hybridized two-way stationary X and stationary Y plus spatial parallelism as well for this gray line here. And you can see the improvements continue. And then finally, I believe we have, when we go four-way stationary X, Y, and spatial, we achieve our peak performance with a significant reduction in the overheads across the board from all the communication libraries. And we're at this is now running on 2,000 GPUs. And just by optimizing the way we decompose the problem and using more efficient collectives, we get a 1.7x improvement for the same size problem. The second aspect of this work is that now we can actually tackle problems that you just can't run on single nodes within the system. So this is a wide ResNet 50, 4x wide ResNet, and this problem didn't run on a single node, on a single GPU. And so we've unlocked even greater network sizes that are available that researchers can now explore. And if we continue this this evolution down here, we can see as we go from data parallel to stationary X plus spatial, and now four-way X stationary X plus spatial, we can see a significant improvement again in the mini batch time at 2,000 samples. And as you see, we have many fewer samples per GPU here because anyway, and finally we can scale this all the way up to 8-way stationary to get a much stronger result. And so you can see is again how we're now this is actually using a stationary W where we have both channel and filter parallelism down here in the blue line. And this is a 4-to-1 or 4x improvement in strong scaling for the same problem size. So the fantastic thing here is that as we're training this, not only are we not getting any loss in accuracy because we're working with a fixed size mini batch, so the model learns the same. We are able to actually tackle problems that we were previously inaccessible. And so here you can see a push from a standard ResNet 50 all the way up a wide ResNet by 4, where we get a measurable 1.5% improvement in top 5 accuracy, almost 3% improvement in top 1 accuracy, and we can drive the training time down by a factor of 4. Okay, so as I said, this is now one more tool in your toolbox when we talk about how do we distribute convolutional neural networks. These things all compose, and you don't want to use any single one too long because it will run out of steam. But we have the combination of a single toolkit that can now provide sample parallelism, where you have this on the left, and this will get you to anywhere from tens to hundreds of GPUs. You can compose that with your spatial parallelism, which we talked about a little bit, and we'll go into another example here in just a moment, where you use halo exchanges to get you another order of magnitude in GPUs in which you can parallelize across. And finally, now the last piece of the puzzle is this channel and filter parallelism, where you can get another order of magnitude in GPUs that you can parallelize across. So that was really, you know, how do we scale up the training of neural networks with a large number of parameters? We're going to jump to the middle category and talk about sample or problems with very large sample sizes where the network activations don't fit on a single GPU, and how we use that spatial parallelism to really make this work. As I said, this was work done originally presented in IPDBS 19, and we've moved on to a new problem here where we've pushed this to an even larger problem. And so this is a slide I often lead off with when I'm just talking about this work on cosmology. And the really sort of flippant question here is, we have very large, you know, we have world-class supercomputers. They are the fastest in the world. Can't we train on some data sets that have very large samples? Well, sometimes the answer is no, unless you have the right toolkit. And so this is an example of a cosmological data set where we are simulating the entire universe. It's a regression problem. Each universe is composed of 512 cubed data volume. There are 4 channels, and each one of these is about 1 gigabyte in size. And so when you put this all together, a mini batch with just one sample can have many tens of gigabytes of memory required for the implementation of that neural network. And so we have to do something. And we took our work that looked at spatial parallelism and pushed this to these 3D convolutional neural networks, which was a really fun challenge to get the distributed GPU accelerated linear algebra working as well. The other thing we're going to show here is that the traditional approach of just partitioning this data and learning on sub-regions of the universe can alleviate the memory pressure, but really discards long-range information. And so I should say that the data set here from the application we're going to talk about is Cosmo Flow, and this is now part of the MLHPC perf benchmarks with the smaller sampled version of the universes, and this is work that please turn that off. That led to, sorry about that. That led to the ability to actually train on the entire universe here. So as we said here, you have the problem dimensions are this 3-dimensional data set. You want to take this data cube, and again, it's like a stencil. So you want to have the halo exchange, and we're going to be slicing the universe into these hyper slabs in the HDF5 parlance, where each GPU has the red slice of this, and we're going to need to be able to communicate those halo regions as we illustrated in some of the earlier diagrams. This is an example of how we've parallelized the Cosmo Flow. This is a sample spatial parallelism with 8 GPUs across 2 different nodes here. So you can see that we have the hyper slabs for each slice of the universe distributed across 4 GPUs. And we have a mixture of partitioning the data, halo exchanges, and then shuffling to collapse the data back into the back part of the neural network. And then we're doing the standard data parallelism across these sets of GPUs. So as I said, one of the hopes for this work was that by using neural networks that could see the entire universe, you could learn something better. And of course, the answer, because I'm telling you, is that it actually works out really well. So what the problem is you have this cosmological simulation, you train a model of, you generate this model of the universe, you want to learn these regression parameters, and in the traditional workflow, you would have to split this data cube into 8 subcubes, each of which was small enough to be able to fit through a standard tool and its memory requirements on GPUs. So this is what you would be able to do with PyTorch or TensorFlow, and is what's in the MLHPC perf benchmark. And this is a fantastic way to train the neural network, but it loses information. In particular, 2 of the 4 regression parameters that we're trying to learn have long-range information. And so when the model is able to see the entire neural network or the entire sample as shown in this top workflow path, what we see is that the network is able to learn, train a model that is an order of magnitude better in terms of the mean squared error for the trained universe, or for the trained model. So let me say that slightly differently. We see the training curve here and the validation curve as we go from 0 to 200 epochs of training. The traditional approach is shown of training on 128 cubed subregions. You can see here that the MSE plateaus or flatlines and ceases to improve past a certain point, while a model trained on the entire data cube can achieve a much more significant mean squared error, both on the training and the validation error. I don't have it in these slides, but if you start to look at the cosmological parameters that are predicted, they have a much smaller variance, and again, a much better accuracy compared to the reference model. And so the quality of the neural network trained on the entire data set is substantially better and enables our domain specialist scientists to use this kind of regression surrogate much more effectively than previously before. And this data set, by the way, is hosted by NERSC, and this work was done in collaboration with NERSC and the work researchers at LBL. So what I'm trying to highlight here is that there are a lot of opportunities when you really push distributed deep learning training to be able to work with larger models and data samples, primarily work with generalized parallel convolution, where you combine sample, spatial, channel, and filter parallelism. It allows you not only to address more memory constraints and train on samples that were previously inaccessible, you can make the models more accurate, and well as strong scale of training time and be able to turn that crank faster. As I said, this work is a lot of hard work over the past couple of years from our research team that's been published at MLHPC, IPDPS, and SC recently. So now I'm going to switch gears and go back to the challenge for large neural networks, where there's a large number of parameters. And I'm going to talk about some work. This is actually by our colleague and one of your colleagues and students, Arpan Jain. He did it over the past summer, where we're going to talk about what if you want to distribute this compute subgraph across multiple nodes. And I want to highlight that this is very preliminary work of just 10 weeks of an internship, and it's fantastic. And it's emerging work in progress. So we have some exciting results, but it's not yet done. But you can go pick Arpan's brain once you can find, well, given that he's back there with all you guys. So the idea for subgraph parallelism is that when you look at these neural networks, shown down here is an example of the ResNext architecture, and on the right here is a transformer model, and this is a collapsed representation where there are these in heads that are the multi-headed attention. And the idea is that if you unroll this, there are these significant compute graphs that are actually very loosely coupled, sort of where they get data and where they inevitably merge their responses into a single result. And so those subgraphs can be done on independent compute resources. And this is work, there's work in the community where Google and others have done some of this parallelization as well. And so we've now been able to integrate this into LBANN, where we're able to compose or start figuring out how to compose subgraph parallelism with all the other forms of parallelism that you're starting to see. So the idea here is that you're going to map these transformer heads to independent GPUs and nodes within an HPC system. And that really means that we're splitting the MPI world into multiple subcommunicators with very distinct branch and synchronization points. These are typically things like a split or slice layer, as well as concat layer or a merge, where we are able to distribute and collect the right parts of the data samples into these appropriate subsets and feed the different subgraphs of the neural network. This is basically a generalization of the group convolution idea. This is actually an example of what group convolution does in the ResNext work. However, this is much more general because it can handle any sort of subgraph within the part once you partitioned it. So it's a more, you can handle more complex subgraphs. This is a work that came hot off the presses about a week ago, or a week and a half, just before Arpan finished up his internship. And the idea here is that we're showing the parallelization of a transformer model in LBANN across multiple compute nodes, each of which again has 4 GPUs. And so the right-hand red bar is the result when you do a data parallel approach. And of course, time on the y-axis, so lower is better. This is a transformer with 500 or 32 heads in it. And what you can see is that going to a subgraph parallelization of 4 or 8 in the blue slash or green vertical bar can be beneficial, although at times the communication overheads will force you to lose performance. And a topological layout of the different subgraphs can, and that's shown in the second and fourth bars, particularly over here, can provide a noticeable improvement for this kind of algorithm. So going back to mapping the communication algorithms to your topology is absolutely a critical need for these kinds of applications. But a real opportunity for how do we combine the knowledge of the domain user, the neural network architecture, as well as the communication library. So as again, this is very exciting early work. It's very exciting, and we've had a fantastic collaboration. So I want to go to the last phase of the talk here now, where we're going to talk about another approach and another problem, which is what happens when you have a data set with a massive number of samples. Now, these samples may be large, they may be small. We're going to talk about a multimodal data set here, but the idea is that this is more at the systematic level, where your parallel file system is actually fairly slow when compared to your internode communication, and you can crush it and bring down an entire HPC system if you do this incorrectly. I know, I tried and crashed all of Sierra one time doing this. And so the idea here is that we're going to talk about an ensemble learning method where you partition the data set, but you're training a single model. And so you effectively can strong scale the training of that. And it required a distributed in-memory training cache as well to avoid crushing the system. This is a different problem that really gets at the heart of a new style of working that we have emerging at the national labs, where we have these very traditional pillars, large-scale experiments. This is an example of the National Ignition Facility, trying to create laser inertial confinement laser fusion with inertial confinement lasers, as well as traditional simulations. So you use high-performance computing and hydrodynamic simulations to know how your experimental facility is going to run. And traditionally, the domain experts have used a small number of scalars of the output of all these to be able to actually predict how the simulation is going to behave, how the experiment is going to behave, and how well it matches the simulation. And this is an area called cognitive simulation, where we are trying to mix in machine learning to help augment the traditional scientific exploration we're doing with large-scale compute, and really take advantage of all the data that's being generated by both experiment and simulation, and bring it to bear for improving the simulations, but also improving our scientists' understanding. I don't have time to talk in depth about the cognitive simulation workflow, although I'd be very happy to offline. That it's an emerging approach to how we mix this all in, all these different components together. But I wanted to take this example of the model that we've been playing with this and talk about how we deal with systems where we have data sets that have over 1 billion images and scalars. So the neural network we're going to be training here is a self-consistent cycle generative adversarial neural network called a cycloGAN. The idea is that we are going to train forward and inverse models that can actually predict to and from a latent space, as well as use an autoencoder to project the image and diagnostic scalars that come out of the experiment and the simulation into that latent space. And then this model is going to allow us to evaluate how simulations are progressing, map simulation results to experimental results, and a whole host of different applications. But it's a fairly complex neural network architecture. But the key challenge that we're focusing on here is that we are able to generate a data set with a really unprecedented size. So this is 100 million simulations of inertial confinement fusion. This was done with a relatively fast surrogate physics model, but as you scale up compute power and look towards exascale, the ability to generate larger and larger data sets is going to just get worse, not better. The goal was to oversample a 5-dimensional input space to be able to actually really aggressively push on how do we develop these cognitive simulation workflows. And so we ended up with a data set that had 4.8 billion hyperspectral multi-view images. So we have multiple viewing angles, we have multiple energies, and we have images and scalars at multiple time steps. And it's packed into a data set with 100,000 sample or 100,000 or 100 samples per HDF5 file. So you have 100,000 files, which again leads to how do you ingest all this data. So you have 10 to 100 million samples. We're going to be playing with one time step of this, so it's going to be 1.2 billion images, 1.5 billion scalars. If you don't do something clever, you're going to kill your metadata servers and your performance. So you need to be able to bundle these up into scientific data formats like HDF5. But now you want to have every parallel rank access a portion of an HDF5 file in order to ensure that we get the right learning and we don't arbitrarily partition the data and the models that see it into bizarre silos of data where models only learn on a region of that data, because this data was generated such that it is sort of a block structured format in the file system. So you want to partition the data set so you can train without loss of generality, and you want to be able to coordinate and optimize how you access all these data files. We're using a tournament algorithm that we developed and showcased most recently at Cluster in 2019. The idea is to let 1,000 flowers bloom, where you're going to train independent instances of a neural network model, but you're going to allow them to teach each other what they know. So here in this example, we have 4 instances of the neural network model being trained. Each one of these has its own internal parallelism, a combination of data or spatial parallelism or all sorts of combinations. So this is nominally being trained on 9 different compute resources. Each one is being trained on their own silo of data. And what's going to happen is that they're going to train independently. So communication happens within this domain of the supercomputer, and then periodically you're going to exchange the entire model. And so in this example, instance 1 passes its model to instance 0. Instance 0 is going to run a held out tournament on a held out set of data to be able to evaluate whose model is better, and then it's going to pick the winning model and evolve it from there. And that model exchange essentially acts as a compressed representation of a different partition of the data. And what we see is that this allows us to, 1, scale up the training on even massive data sets that are otherwise unavailable to be trained on sort of a single instance of the neural network. But what we also see here, as shown here, is that the quality of the final model is improved by this tournament algorithm. And this really occurs because you're getting a broader diversity in the initialization space. You're getting a better distribution of the random numbers as they do the data augmentation. and pulling for different problems. But really here, if we look at the quality of model where lower is better, so this is the error where a single trainer trained is the black line here. As we go from 8 trainers all the way up to 64 trainers, and we look at their behavior as we go over time, the number of steps on the x-axis here, we see that the best model from an ensemble with 64 coupled trainers is in fact better than any instance trained on any instance of the data set trained with fewer trainers and less data. This is really showing some of the challenge here for how do you scale up the data ingestion. So this is basically showing for a number of GPUs going all the way up to 16 GPUs. So this is looking at what happens with a single trainer. This is the time it can take to fetch the data for a single epoch and compute a single epoch. And if you just show that this is showing the data here in blue, if you just load the data and then light blue in steady state, if you don't do something clever, you are absolutely dominated by the time it takes to ingest data every time through the neural network. And so we use parallel HDF5, MPIO enabled parallel HDF5 to be able to ingest the data and preload it. So the idea here on the far right is if you look at dark green and light green, if you preload the data, say here for 8 GPUs, that means do it before, ingest the data at once in a coordinated fashion, and you then look at your steady state epoch time, you get a much faster result where you are now entirely compute bound rather than IO communication bound. This is showing the performance of the model training with this is only a portion of the data set. 120 million images, 150 million scalars was used. This was scaling all the way up to 1,000 GPUs. And what we're showing here in the blue bar is that as you increase the number of trainers, and you can actually decrease the training time because each trainer is looking at a smaller set of the data. But we're going to couple that with the next chart here, which shows that as we increase to 64 trainers shown in red here, the validation loss of the final trained model does not degrade as it would if you just did a normal ensemble. So the quality of model remains the same or improves with this training technique. So what this allows you to do is this kind of tournament method allows you to partition the data set and couple an entire HPC system for training a single model without having tightly integrated communication at every single step of the training phase. And I see I'm running out of time. So we have run this at the full 100 million data set sample with 1 billion images and scalars. We've also incorporated some challenges or encountered some challenges where we have communication errors that we're still debugging. And debugging at that scale is, of course, quite fun. So just to summarize, what I want to hammer home is that efficient communication enables us to train models that were previously inaccessible on data sets and sample sizes that were just out of the reach of previous generations of researchers, and that the scientific applications that we're pushing at really demand these kinds of approaches. I've covered ways to distribute convolutions over filters and channels as well as spatially, subgraph parallelization across multiple nodes, as well as on a tournament method allows you to loosely couple large numbers of compute resources on an entire HPC system. We are being driven by a number of different applications, from advanced therapeutics for medicine, work on nuclear nonproliferation, the ECP candle and XLearn efforts, where we're looking at the behavior of RAS proteins binding with lipid membranes. As you saw, work on cosmological models and other sort of surrogates, all the way to developing cognitive simulation for inertial confinement fusion. And then finally, I'd like to say again that none of this work would be possible without the fantastic team of researchers, developers, graduate students, and collaborators that we've had the opportunity to work with over the number of years. And with that, I think I'm done and out of time. So thank you very much for the opportunity to speak to this at this conference.
Brian, thanks a lot for your exciting talk here. There are two questions. If you click on the Q&A box, either you can do that or I can read it out.
Okay. So I think the first thing in looking at this, at the translation to this, in looking at translating this to a practical implementation in the non-academic setting, how does the different tiering models and approaches compare to a price saving? This is important given the per unit cost of compute resources in a service model such as Azure and others. So that's a great question that I am actually, that has not been the focus of our research or analysis. So you're right. If you are doing this in a commercial setting where you're paying per compute hour and per node hour, then you need to ask yourself whether or not the science and researcher time is significant enough in terms of savings if you're going to be able to get to a trained model faster, or allow them to learn that a neural network architecture they're pursuing does not actually solve their use case sooner. So really, a lot of our work has been driven from a scientific and mission need to get to reduce time to solution. And so as long as that's a driving cost for a commercial organization, I think these approaches would still work very well. As always, these knobs here are really quite flexible, so you can choose how many compute resources to run. I will say that we haven't done a lot of benchmarking on cloud-based systems such as Azure or as Amazon and whatnot. One, because at a national lab, we have a much more, we have native resources that we can use, but we've really tuned for that best low latency interconnect. And so I would be curious to see how well this would perform given the cost of that. On slide 43, why is the validation error fluctuating so much? That was on the Cosmo full neural network. That result was from an earlier training pass on the neural network where we saw a lot of that. We've since done a lot of hyperparameter tuning on the learning rate, and we have that pushed down. I didn't get a chance to pull an updated figure for that slide, but it's a fantastic catch. Thank you for paying attention.
So are there any other questions? If people have any questions, they can follow up on the Slack. So thanks again, Brian, for an excellent and thought-provoking talk.